We are now ready to compute the Mobius function in the lattice of non-crossing partitions. And because of the canonical product decomposition, it suffices to compute the Mobius function at just the points 0 and 1, the least and largest elements. So I'll call this gamma n minus 1. The reason for this shift in indexing will become clear later. But we have gamma n minus 1 defined for n greater than or equal to 1. Gamma 0 is equal to 1. And we'll use Weisner's theorem with a equal to 1 to n minus 1 and n, a two-part set partition, which is obviously non-crossing. And what we get is gamma n minus 1 is minus summation x meet a is equal to 0 hat, x not equal to 0 hat, mu ncn x comma 1 hat. So far we've just used the statement of Weisner's theorem, and as before, the set of x for which x meet a is 0 hat, the discrete set partition, means that x is of the form xi, where I write xi is a set partition where everything is its own block except for I, which is clubbed with n. And for I from 1 to n minus 1. So now what Weisner's theorem gives us is gamma n minus 1 is minus summation I goes from 1 to n minus 1 mu ncn xi comma 1 hat. But now I can take this xi comma 1 hat, this interval. This is isomorphic to the interval 0 hat comma phi xi. So let's compute what phi xi looks like. And to compute phi xi, let's just draw xi as a non-crossing partition. So you've got 1, 2, 3, 4, all the way down to I. And then you've got I plus 1, I plus 2, all the way up to n minus 1, and then you have n. And in this set partition xi, there's only one block of size greater than 1, namely the block containing 1 and I. To compute phi xi, let's use the usual procedure 1, 2, 3. We write them between the numbers in the earlier diagram, and now we see what the connected components are. And here we see that n, 1, 2, 3, 4, all the way up to here we have I minus 1. These are all in the same block. And then there's another block which contains I plus 1, all the way up to n. So what we have is that phi of xi is the set partition with two blocks, 1 up to I minus 1, and then also contains n, and the other block is I plus 1 up to n minus 1. And so we can conclude that xi comma 1 hat, which is isomorphic to 0 hat comma phi xi, is actually isomorphic to nc. This block here has I elements and this has n minus I elements. And so we can conclude that gamma n minus 1 is minus summation I goes from 1 to n minus 1, and then we have gamma I minus 1, gamma n minus I minus 1. And renumbering both n and I, this gives us gamma n is equal to minus summation, and now I change the I also. I goes from 0 to n minus 1 gamma I gamma n minus I minus 1. So from this recurrence relation, we can compute the gammas. So we already know that gamma 0 is minus 1. Gamma 1, well, this tells us that this is just minus gamma 0, which is minus 1. Well, gamma 2 is actually minus gamma 0 squared, which is minus 1. This is minus gamma 0 gamma 1 minus gamma 1 gamma 0, which turns out to be plus 2. Gamma 3 is minus gamma 0 gamma 2 minus gamma 1 squared minus gamma 2 gamma 0, which turns out to be minus 2 minus 1 minus 2, which is minus 5. Gamma 4 is minus gamma 0 gamma 3 minus gamma 1 gamma 2 minus gamma 2 gamma 1 minus gamma 3 gamma 0, which turns out to be 14. These are signed versions of what are called the Catalan numbers. And Catalan numbers can be defined in many different ways, but here I'll stick to a rather boring and straightforward way. C0 is defined to be 1 and Cn is defined to be a sum over all I goes from 0 to n minus 1, Ci Cn minus I minus 1. The unsigned version of the identity recurrence relation defining the gamma n's, and you get that the Catalan number C0 is 1, C1 is 1, C2 is 2, C3 is 5, C4 is 14, and so on. And the upshot is the following conclusion, that the Mobius function of the lattice of non-crossing set partitions of 1 to n at 0 comma 1 is minus 1 raised to n minus 1 C n minus 1, given by the Catalan numbers. We'll see these Catalan numbers again and again as this course progresses.